We're doing applied exponential functions in this video. So this is the growth and decay topic. There's a few little tips there, and we'll see how we go. So we've got this carp population here, and there's the population equation, 50 times 2 to the power of t. Now, if you want to find the initial population, you can write this as p brackets 0, so that would mean that t is 0. And this is 50 times 2 to the power of 0, which is just 50 times 1, or 50 carp. So if you ever want to interpret these equations, that number there is your initial value or initial population, starting value. This number here turns out to be the percent increase or decrease per time interval. So because that is a 2, this population will be doubling each year. That's how that works. So for example, at year 0, we got 50 carp. At year 1, I can tell you we'll have 100 because it's doubling each year. But let's see if we can check that. So we can go 50 times 2 to the 1. That would be the equation there. So this is 50 times 2, which is 100. Similarly, we can go 50 times 2 squared, which is 50 times 4, or 200. So it's 200 there. The other way that you can fill out a table like this is to graph it on your calculator. And I recommend graphing on your calculator for every question in this topic. So go into graph mode. Our equation was 50 times 2 to the power of, and we're going to use x instead of t. We'll draw the graph there. Not getting a good window, but here we can sort of use this table to help. The years tend to go up very slowly, so maybe we'll only go up to 10 years. The population will grow very quickly, so maybe let's look at 5,000 carp and see if that gives us something sensible. Yes, it does. So that's what our exponential graph looks like. So if you go trace at 0, you'll see y is 50. If you go trace at 1, you'll see y is 100. And trace at 2 should give us 200. So you can actually just keep tracing. So trace at 3 would be 400. Now I know you can probably see already that it's just doubling, so it's easy enough to work out the number. When these numbers are a bit messier, it's not super easy to do that. If we want to sketch the graph, so it can be a little bit tricky to sketch the graph just with the scales and everything. But we're just going to go 1, 2, 3, 4. I might go up by hundreds in the axis there. So 1, 2, 3, 4. You don't need to write in every axis mark, but sometimes I just write in like 500 and then 1,000, just like that. Similarly, I just write in like 5 and then 10, like that. We've got to go t in years for the x-axis, and we've got to go population in carp for the y-axis. And we're going to put a few points on here that we know. So we know 0 is 50, 1 is 100, 2 is 200, next one is 400, and the next one is 800. And then the graph should sort of look like that. And we can label it P of t is 50 times 2 to the power of t. So that's everything your graph needs. Make sure you've got all that stuff. And what's the population after 10 years? So there's two ways to do this. You could go P of 10 is 50 times 2 to the power of 10 and get an approximate for that. Or you can go trace and then you go x is 10 on your calculator. I'd recommend the latter, the trace method, just because it's quicker. So if you go trace and type 10, you'll see 5, 1, 200. So 5, 1, 200 carp. And that would be the answer you get there. So probably this method is okay, and this method is really good. Make sure you do know both though, because they can both come up. Okay, how long will it take for it to reach 5,000 carp? So what we've got to do is we've got to solve P of t equals 5,000. And we will learn tools to solve equations like this, but for this topic, we're just going to do it on the calculator. So we're going to go gsolve and go xcal, and you're going to go 5,000 for the y value. You can see that it's 6.64. And if you want to check and make extra sure you've got it right, you can just go trace and type 6.64. You should get y is about 5,000, down to some rounding, but we give 3 significant figures. It is not reasonable for the population to grow like this forever. There would be some limiting amount, usually related to the size of lake and resources available. Like, we predict 51,000 carp. I don't think 51,000 carp are going to fit into a lake. Well, depends how big the lake is. But then that would double the next year to 100,000, and then 200,000, 400,000. So eventually you are going to hit a limit. So the graph actually would look something like this. So it would start off exponential, and it would sort of reach like some limit there. The graph that I just drew there is called a logistic function, which shows up a bit in year 12. Okay, next we've got a model with exponential functions, so we need to find the equation. So we've got A, the amount of money in my compound interest account, and it's going to be 2,000, so that's the starting value, times some mystery number to the power of t. And just as a reminder, that is the start value, and this would be the percent increase, decrease, or like what I times it by each time. So basically, I need to figure out what did I times by to get that. You'll notice with the carp question here, you were timesing by 2 each time, and that's how there was a 2 in the equation there. Okay, so let's see if we can do that. Probably the easiest way is just to go 2005 divided by 2000 on your calculator. So it's 1.0025. And this would be 2005 divided by 2000. So we can actually fill out the rest of the table. If we go 2000 times that number, 1 times, not plus, 1.0025, I get that. And if I times it by it again, I'll get my next number, 2010 and 1 cent. If I do that again, so times 1.0025, we're going to get 2015 and 4 cents. And then if I times it again by 1.025, I'm going to get 2020 and 8 cents. So you get these few extra cents on the end, and they will stack up eventually. Compound interest is really good like that. I want to really point out, we just did a compound interest problem without ever knowing the compound interest formula that you may have learned in previous years. And that is the power of doing a subject like methods, is that you learn really general concepts like exponential growth, and then they have a range of applications like populations or compound interest or radioactive decay. And you don't need to learn specific formulas for each situation because you understand the exponential growth that's happening under the hood. Okay, so we still need an equation. So I think we've got it. A was 2000 times 1.0025 to the power of t. And the way that you can interpret this number is that you can move the dot. Well, this is like 100.25% if you want it as a percent, but the increase is 0.25% increase per month. So that's how this bit works. And then, I said it before, but that is the starting value. So that would be the equation there. And you could graph it to figure out like how long it would take you to hit a specific amount of money in your account, for example. That would be similar to this question for the carp. Okay, model a radioactive substance starting there and losing 10% of its mass each year. So if we model this, so I'm going to have 500 grams right up the top, and I might put 250 grams in the middle. So 150, 150. So each increment there is going to be 50 grams. And then we'll just put the years here. So 1 up to 5 and 10 years. So we're going to start at 500 grams, and this thing's supposed to lose 10%. So what is 10% of 500? Well, you can go 0.1 times 500 to get 10%. So that's 50. So I would expect maybe after 1 year, I'm at 450 grams. Because I've lost that 50, which is 10%. Now that was a little bit slow to work out because I had to do a few different steps. What's nicer is working out what the 90% remaining is. So if we go 0.9 times 500, you get 450. And if I times that by 0.9 again, I should get the next answer. So 405, a little bit above 400 there. And then if I times that by 0.9 again, 364. So we're looking maybe up here. So the equation is, I'm going to say M for mass. This is 500 is the starting value, and we're timesing it by 0.9 to go forward a year. And I might write this as a function of time. This is a function of time. Okay, now I could ask a follow-up question. The half-life. So this is the time taken for the mass to halve. And then this is how long till 250. Because we started at 500, we'd like to get to 250. Okay, so we can work that out. If we graph this, so just going into graph there, our graph was 500 times 0.9 to the power of, we'll use x instead of t. And we can draw that graph. We don't want our carp window. We'd like to set the y max to, let's go a little bit over 500, so 550. And you can see here that the calculator should hopefully agree with me. So if I go trace and I go 0, the y value will be 500. If I go trace at 1, 450, trace at 2, it would be 405 like we discussed, and trace at 3, 364. So how long would it take to get to 250? So that would be in GSolve xcal 250. 6.57 years, 6.58 years. One thing that I want to point out about the half-life is that it's very counterintuitive. So I'm going to make my window a little bit bigger. We'll go up to 20. So the half-life is 6.58 years. If I go double that amount, so that would be 13.16. That's 2 half-lives. I've halved twice. So I should be at about 125 grams, which I am. You can see the Y value there. And you'll notice that no matter where you start from, so even if your thing started at 400 and you waited till it got down to 200, that would still take 6.58 years. So it doesn't matter where you start from with radioactive decay. Some more examples of decay are like temperature, if we're like cooling a substance. And that's going to be really useful for figuring out, if you put something in the freezer, how long it's going to take to cool down to certain temperatures. The other thing that I will mention is radioactive material usually takes a long time to be safe. You'll notice that this graph will never hit 0. It does get quite close. If I make the window go out to 100 years, you can see the graph does sort of go down towards 0. And eventually it's going to be so small that it's safe. But that takes a really long time to happen because of exponential decay. The other thing is with the rabbit population, that sort of does the opposite. It grows really quickly. So you can see that when, for example, we had COVID, people were really worried about this bit there when it was only slow growth. And if you're not familiar with exponential functions, you're like, oh yeah, this is fine. It looks like it's sort of going to do that and we'll be all good. It'll grow really slowly. But because diseases spread exponentially, mathematicians get very spooked when it gets there because they know what's going to be coming later on the graph.